Hello, everyone. Sorry for the delay. Can you see? I'm not sure I'm sharing the screen. I'm not sharing the screen.
No.
Just see you.
So we will probably extend
Okay.
a little bit.
Okay, now you should see the screen, right?
Yes.
Okay, thank you. All right, so we have seen that we are able to come up with some operations that mimic the classical spatial convolution in the Euclidean domain. We can simulate them in the non-Euclidean domain. We have seen that we can do the same for the spectral convolutions from the Euclidean to the non-Euclidean domain. And we said that in this latter case, learning the convolutional filters means learning their Fourier coefficients. These are the Fourier coefficients of the convolutional filter. This is what we want to learn. And we said that this doesn't really correspond to a true convolution. The result will not be shift equivariant. So this is not a true convolution. And another very important aspect is that these Fourier coefficients, of course, depend on the basis, on the set of Laplacian eigenfunctions that we computed before. If I change the basis and I still use these Fourier coefficients, they don't make any sense, right? So they depend on the basis. They were computed by taking the inner product with a specific basis. Why am I emphasizing this fact so much? So this is the problem. Let's say that I have my geometric object, for example, the 3D horse, or for example, the Twitter social graph, and I learn the operation that, I don't know, computes the edges of some function defined on the horse. So I have this neural network that is able to identify the edges. You see, so this is the function. These are the edges, and this is a spectral filter. So I learned the Fourier coefficients of the convolutional filter that gives me this result. And I do this on this particular horse shape. Imagine this. So I have this particular horse shape. I do my learning there, or I have this Twitter social graph and I do my learning there. Now, whatever I learned on this horse, I want to apply to a different horse. Whatever I learned on the Twitter social graph, I want to apply to the Facebook social graph. So I'm going to change the geometric object. So, and I'm hoping that if I change the geometric object, then the spectral coefficients that I learned on the former case will still work in the new case, in the new geometric object. Now, this is not going to happen. Okay, so now I'm going to show you an animation where I replace the original horse with several different versions of the horse. And I show you simultaneously the action of the learned filter. So this is what happens. You see, so each frame of the animation is a different horse. And when I apply the learned filter on these different horses, I don't get something that looks like edges of a bumpy function. You see, this is not really working. So these filters do not transfer over different data. Similarly, you can expect that whatever you learn with this method, whatever you learn on the Twitter social graph, cannot be transferred to the Facebook social graph, or even to the Twitter social graph 1 week from now. It will be different. So this spectral convolution, in other words, can only be applied whenever you know that your domain is going to stay fixed. The domain is not going to change. All right. So it is a different notion than generalization over different images that we have with classical deep learning. So classical deep learning, say you train on a collection of photos of your dog, and then you want to apply what you learned on photos of different dogs. So that generalization does not involve the structure of the domain. Okay, so that's a generalization over the set of features defined on the domain. Instead, this is generalization over the domain itself. Okay, it is a different notion that in 2D we don't have at all. Okay. Very good. So, but whenever you have a fixed domain, you can use this spectral convolution. Now, unfortunately, I'm sure that many of you have heard about graph convolutional networks. So you can, if you look for graph convolutional networks, you will see a lot of tutorials and lectures and papers explaining their properties and so on and so forth. They are part of this family of methods. Okay, so they can be applied to one fixed domain. You cannot change the domain. Well, unless you do certain modifications, of course. Now, let me show you how these graph convolutional networks and related approaches actually work. So the idea is the following. They work on a graph. So instead of considering the Laplacian of a mesh, we are going to consider the Laplacian of a graph. So look at the formulas. We have 1 along the diagonal, and then for connected nodes, we have 1 over the degree of that node. For meshes, we have on the diagonal the sum of the rows, so the sum of the elements along the row for each row. And off diagonal, we have some scalar value associated to that connection between nodes. So these are very similar, because along the diagonal, we have the sum of the rows, right? So D is the degree. So if you take the sum over all nodes, we have exactly 1. And off diagonal, we have some value. Okay, so the form is exactly the same. So the graph Laplacian can be seen as a special case of these cotangent Laplacian that we have with meshes. Okay. Okay, very good. Now, so of course, so just to reconnect with the question from before, the graph Laplacian, you see, it is defined as a matrix. So it is by construction, it is a linear operator. Okay, so it is not a non-linear Laplacian. It is a linear operator. Now, with this in mind, let's try to see some more interesting properties on the spectral convolution. Okay, so we are going to see something that maybe we do not expect. So once again, let's consider a mesh, or if you want, you can also replace the mesh with the graph. And instead of the Laplace with the cotangents, you use the graph Laplacian over here. So how does it work? How does the Laplace operator act on functions defined on this domain? So this is what happens. If you take a function x, you multiply it from the left with the Laplace operator, and then you look at the ith dimension of the output, then it is the same as computing this summation. J goes over the neighbors of I. So J goes over the neighbors of I. For each pair ij, we have a value. It will be cotangent for meshes. It will be 1 over d for graphs. So 1 over 6 in this example. And then we have the difference of the input feature computed at j and computed at I. So this is equivalent to applying these metrics to a vector x. This is exactly how it operates. This is also equivalent to applying these metrics to a vector x. The only difference will be the w. Only the w changes. Very good. So if we look at this way, we see that the Laplace operator is a local operator. Of course, we already knew this from the continuous analysis, right? We used local operators, divergence and gradient. So it is a local operator. We see it even more clearly in the discrete setting. And of course, this is computing. This is matching with the intuition we had before. So this is if you look closely at the formula, it is taking the difference between the weighted average of the neighborhood, so weighted by W, and the value at the current vertex. This is the geometric intuition we gave of the Laplacian. Now, we have also said that the eigenvectors of the Laplacian gives us a way to compute the Fourier transform. So we can compute these dot products of a given vector x, a given function x, with the phi, and we get the Fourier coefficients. And we have also said that the convolution turns out to be an operation of this form. I skipped all the algebraic steps before, but this is the final result. And we said that when we do spectral convolutions, we are interested in learning or solving for the values of these y along the diagonal. These will be the coefficients of the convolutional filter. So this is what we've seen until now. Now there is something we can do, something very smart actually that we can do. So instead of letting these Fourier coefficients, which we are solving for, instead of letting them completely free to take any number, any value, or without any special parameterization, we can decide to express these numbers as some transformation of the eigenvalues of the Laplacian. Okay, so we can say, well, I want the y1 to be, I don't know, the 10th eigenvalue squared. Okay, so some transformation of the eigenvalues of the Laplacian. So this is, in other words, we can say that we can parameterize the filter by the eigenvalues of the Laplacian. Okay, so this is what's happening over here. Okay, so this is just replacing the same expression as before, but instead of this y hat, I'm writing a diagonal matrix tau of lambda, where tau is a nonlinear transformation of lambda, and lambda are the eigenvalues of the Laplacian. So what we want to learn the tau. Okay. Now, of course, by following the principle of neural networks, we can let tau be a neural network. So the transformation that we apply to the eigenvalues is going to be parameterized by the weights of a neural network. Okay, tau of theta, and theta are the weights we're looking for. So now, instead of solving directly for the coefficients of the convolutional kernel, we are solving directly for the parameters of the transformation. For example, a popular way of parameterizing the coefficients is by just taking a polynomial of the eigenvalues of the Laplacian. So you take the eigenvalues squared, the eigenvalues cubed, and then you have to learn the combination coefficients of these powers of eigenvalues. All right, so of course we all know that if we take this decomposition, phi lambda squared phi transpose is equivalent to taking the original operator L squared. Okay, so this is the way you compute matrix powers, meaning that a polynomial of the eigenvalues corresponds to a polynomial of the operator itself. So these learnable spectral polynomial filters are actually not spectral at all. You can equivalently compute the powers of the eigenvalues by taking powers of the operator. You can just multiply delta by itself k times. This is something you can do once and for all offline. So you have all the powers of lambda, of delta, of the operator Laplacian, and then you only have to learn the coefficients of the combination. Usually, how many powers do we have? Do we have 100 powers? So do we have 100 coefficients to solve for? No, usually people have been using 2 or 3 at most powers. So 2 or 3 at most coefficients to solve for. Okay. So this is what today is called the spectral convolutional networks on graphs. They are called spectral because they come from these arguments. But in practice, they are not spectral. They are computed in a spectrum-free way. We just take powers of the Laplacian. And of course, since we are considering one specific Laplacian, considering the specific Laplacian of a network, these can be applied only to that network. I will come back to this with one application later. All right, maybe you have heard of ChebNet or Chebyshev-net. It is one such model in which instead of using these plain polynomials, they use other kinds of polynomials, the Chebyshev polynomials. It is not so important, just to give you a pointer in case you have heard about ChebNet models. Yes? Ismail, is there a question? Okay. Very good. So this is now interesting because basically, if you think about it, what we have done by doing all these steps is replacing the notion of convolution. So we started from trying to simulate the spectral theorem, well, the convolution theorem from Euclidean spaces. We started from there. And then we did all these reasonings, and then we come to just a simple application of the Laplace operator or polynomials of the Laplace operator. So we are replacing the notion of convolution with the notion of applying some local operator, such as the Laplacian. If you look at GCNs, the famous graph convolutional networks by Kipf and Welling, they are basically this. They are just applying the Laplace operator to the features. So that's it. So in this sense, they are replacing convolution. In this sense, they are convolutional networks. Okay, so this is the reasoning that we should follow. Now, of course, you can apply all these also to other structures. Basically, whenever you have a notion of proximity between points in any space, even high-dimensional space, as long as you have a notion of proximity, you can construct a combinatorial structure like a graph. So if two nodes are close according to some notion, you can construct an edge that connects them. Or even other combinatorial structures. You can construct a hypergraph, a simplicial complex, and some other structures. Once you have the combinatorial structures, you can compute a Laplacian. Once you have a Laplacian, you can do these kind of convolution. Okay, so this idea in this sense extends to point clouds, for instance. You can compute a graph starting from the distance between points in your embedding space. And then you can apply this convolution. So this is a very powerful idea. It doesn't require you to have a 3D shape or anything that is low dimensional. You can have your very high dimensional embeddings and do this convolution there. All right, so let's look at a few applications. I'm going to try and be a little bit quicker, even though maybe I do have enough time. Okay, so let's look at generative models. So I'm sure you know the idea. So the idea is that you're given some training samples, I don't know, images of faces. So let's look at this example. You're given images of faces. They behave according to some distribution in the data space. And then you want to be able to sample new samples from this distribution. Okay, so from the examples, you estimate the distribution, and now you want to estimate, you want to sample a new example, so a new face. This is, well, by doing this, you are designing a generative model. If you're able to do this, you are able to generate new examples, so new faces. In fact, what you see here, these are not training samples. These are completely new generated faces. So if you visit this website, this persondoesn'texist.com, you will have a lot of such examples, and they are completely synthetic. They are completely generated. So you can already see that generative models can be very powerful. So in 2D, we have already seen a lot of very interesting results. Now the idea is, can we bring these over to the geometric domain? Can we generate molecules? Can we generate a new 3D shape? Can we do this? we are still working on it. So we as a community, I mean, we are still working on generative models. There is a lot to explore, a lot to discover. I will give you a few pointers today. So the basic idea is that, first of all, well, you can follow the recipe that is standard for images, and you can construct models such as autoencoders. Okay, so you have your input object. In our case, it is a 3D shape or a graph. In the classical case, this would be an image. It goes through some encoder. The encoder outputs some latent code that compactly represents the input. So you have a latent code. Since you have one latent code for each shape, all of them together, they form a latent space, which you can explore. You can sample the latent space and then decode back to the data space. Okay, so and the decoder part, actually the sampling plus decoder part, is a generative model. Okay, now when you train this model, encoder, decoder, you call it autoencoder whenever the loss you minimize is the reconstruction loss. So at training time, you're trying to learn the weights of encoder and decoder such that going through the encoder and back through the decoder gives you exactly the input that you started with. Okay, so if this happens, this is written here in the loss, then you call this an autoencoder. And of course, you call this the reconstruction loss. The decoding of the encoding of X should be equal to X according to some norm. Now here I'm using Frobenius norm just for simplicity of explanation. In case of 3D shapes, there are several useful notions of norm that you can use here. By the way, this has been done surprisingly very recently. Actually, the first attempt I am aware of is only from 2017. Okay, so doing an autoencoder for meshes. So the results were, I don't know, reasonable. Okay, so you have these shapes that are completely new, completely generated from the learned latent space. But well, these were actually not the desired output. For example, you see that there are distortions. So like the arm is actually self-intersecting. That is not reasonable. And the pose also, the pose you see, they are very close to the poses that they have seen at training time. Okay, so it is not really generalizing well outside of the space seen at training time. We call this out of distribution generalization. But this was the first attempt. Now it seems like we can do something, right? So you can actually have a generative model for 3D shapes. And then we will see about graphs later on. Can we improve this result? Can we do something that is specific to the 3D setting? Because until now, nothing was specific to the 3D setting. This is just a classical autoencoder model that we already use for images. Okay, so can we do something more? So let me skip this part. Can we do something more? This is actually the second question over here. Can we impose some proper geometric behavior? Can we avoid self-intersections? Can we avoid crazy, impossible poses? Can we do something like that? All right, so actually, yes, right? So now we have geometric information. We have a geometric 3D shape. We have all the tools of differential geometry, of geometry processing, of 3D shape analysis. We have all of that to actually try and regularize the behavior of the generative model. So we can do something about it. So this is something that we thought of 1 year ago, and this I promise this is the only thing that we did that I'm explaining today. So the reasoning is the following. In geometry processing, there is a very well-established line of works on exploring the space of shapes. So imagine you have an elephant model taking all possible poses. Okay, so all the possible poses of the elephant model can be modeled as a space where each point is a pose of the elephant. Okay, so it is an abstract space, very high dimensional space. But if you're able to do this modeling, then maybe you are able to compute, I don't know, shortest paths on the space, and that would give you, ideally, that would give you all the intermediate elephants that go from this pose to this other pose. Okay, so this is sampling the shortest path, the geodesic, on the space of shapes. So this has been done. This is a true result. This is from 2014. I'm not going into the mathematical details, but this is a very well-defined process. So everything is solved for by optimization. There is no learning. This is very hardcore geometry processing. Okay. And also, well, something cool you can do, you can also keep walking across the shortest path. So keep walking along the geodesic, and you can extrapolate new shapes. Right. So, and these, to me, this is a generative model, right? Because I'm sampling the space of shapes and I'm generating new shapes. So the orange ones are new shapes. So we thought, well, these we were able to do before. So why can't we bring these intuitions and these instruments into generative models for 3D shapes, right? All right, so let's see how we can do this. So one thing that I want to emphasize here is that what I called the shortest path, going from the gray elephant to this other gray elephant, this is actually minimizing a measure of distortion of the surface. So in this sense, they call it a shortest path, because this is from here, from the first one to the second one, this is minimizing the stretch of the surface. Okay, stretch and compression is minimized. Okay, so there is an energy, well-defined energy, that they are minimizing when they define the geodesic, when they define the shortest path. Okay, so, and this measure is a measure of metric distortion. All right, now this is why we're interested in what we call metric regularization. Can we impose such behavior on a generative model? In other words, something that we might want to aim for is the following. Imagine that this on top here, that this is our latent space. Okay, so I'm just representing it as a collection of colored dots just for easy of interpretation. And now we're sampling two shapes, the green one and the blue one. So we are sampling these two latent codes in the latent space. Now we want to do the following. We want to take a linear interpolation in the latent space. You see this straight line, this is a linear interpolation, and then decode a sampling of this linear interpolation. So we want to decode all these new shapes in between. And we would like this linear interpolation in latent space to correspond to a linear interpolation in the metric space. So basically, we want the sequence of deformations that brings me from here to here. We want this to be as isometric as possible. So we want to minimize the metric distortion that goes from here to here, from here to here, from here to here. Okay, so we want to minimize the overall metric distortion. So this is what we want to do. I haven't told you yet how you can do this. Actually, well, okay, so linear interpolation in latent space, we want it to be equal to a sequence of approximate isometries. This is just language. So we want to minimize the metric distortion. How to do this? Super easy. So here, let me show you the loss. So without going into all the terminology. So the idea is the following. The loss is enforcing that taking an interpolation of latent codes and then decoding the result should be equal to just interpolating the geodesic distances in data space. Is exactly what is written here. Taking the latent codes, taking an interpolation of the latent codes and then decoding the result should be equal to taking an interpolation of the metric. It is written here. where is the metric written? Just the matrix of pairwise distances. Okay, so pairwise geodesic distances on the 3D shapes. If you take all of them, all the pairwise distances, that's a full encoding of the metric of your shape. You see, if you look at this function, if you look at this loss, this is going to be our interpolation loss. Well, it is very simple, right? And it is enforcing that behavior. If you go and try, very easy to implement. It's very easy to implement. If you go and try this, and then you only train your resulting autoencoder, if you only train it with this loss and only this shape and this shape, if you try to sample from in between the two shapes in the latent space, this is the result you get. You see that the behavior is very natural. It is very natural because at training time, we asked for this kind of behavior. We asked for a smooth and nice interpolation of the distances. There are technical aspects to take into consideration here, of course, but more or less, this is the idea. Extremely simple, and you see that this is something that, if you're dealing with geometry, is actually easy to realize. If you're dealing with images, if you want a photo of yourself and then a photo of yourself smiling, and now you want your generative model to generate all the intermediate facial expressions in the photo, well, that's going to be much more difficult. At least this is my feeling, because we don't have direct access to the metric of the object depicted in the photo. We don't have that direct access. If you deal with geometry, we have a lot more richness in information that you can exploit. So this is one way to exploit it. All right, well, you can use it for several applications. I'm going to skip this. One curious behavior that is always, actually very often observed in autoencoders is this analogy algebra. So in natural language processing, I don't know if you heard of this, but in NLP, if you work with word embeddings, so you have some high-dimensional representation of each word from a dictionary, a king, of a man, of a woman, and so on, then you take these representations and then you algebraically compute king minus man plus woman. Surprisingly, you get the word embedding for queen without even asking for it. This is something you get for free in certain models working with word embeddings. Okay, we tried this with our latent codes for the 3D shapes. Take the latent code of this person minus the latent code of the same person in a different pose. We sum the latent code of a different person in this pose. We get the latent code of the person in the first pose, but with the style of the last one. Okay, so it is, you can look at it for yourself, right? It is reproducing this analogy. King minus man plus woman is queen. This individual minus this neutral plus this neutral get this individual in this pose. Okay, this we get for free, and we get a very nice shape because the latent space is regularized. Okay, very good. So something else you can do. This is called problem.
Sorry, question.
Yes.
When the last example of the NLP is the king and the queen, does it have to do anything with inheritance?
So you're talking about like taxonomy in the definition of words?
I'm talking about like in this embedding, this concept, is it connected to what is called in what is it called, the Sharp, the software in not symbolic programming, inheritance of property? Like I say king and I say man. So already I define some space of properties, right? Now, if I do minus man, but I still talk about king, so now I inherit a property of, say, called the royalty. Now I assign a woman to the royalty, of course I get queen.
Yes, so this is most
That's
likely what
logical,
it,
right?
also I agree. That's a nice observation. That is most likely what is happening. But what is remarkable is that we didn't feed the network with these properties that you are mentioning. You just show the network words, simple words, and it learns on itself, by itself, this notion that you are mentioning.
But the way it learns, it's probably via some kind of inheritance or...
Probably, yes. It discovers by itself the notion of inheritance. Yes, I agree. I agree.
So can I take it one step further and ask you, what would be the connection between embeddings and projection? Because I see some connection between the inheritance and the projection. Because if I project a line on a plane, I get from a line, I can get a point. Okay?
I see.
If I do a projection.
Mhm.
So now I look at that point, and that point inherited some properties of the line which was projected onto that plane.
Mhm.
Am I confused or confusing?
No, I think you have a very sharp intuition. I think that's a clear statement. But I also feel that what you're asking is precisely the problem of representation learning. So there is this area called representation learning that is concerned with answering and studying these questions. So I see what you mean. Yes.
Okay, thank you.
You're welcome.
Can I also ask regarding the picture you're showing now?
Mm-hmm.
If I omit the metric regularization, if I use a plain variational autoencoder, do you have an intuition how would the result look?
Okay, so I had that slide, I removed it. You still have this behavior, which is basically like inherent in variational autoencoders, it seems, but the shapes suck. But
okay.
the behavior
The shapes
still have it.
become more ugly as we saw them before
Yes.
in this 2017 work. Thank you.
Yes. Okay. All right, so disentanglement. So disentanglement is again a very general notion, again from representation learning. Okay, so let me give you a couple of examples of what we mean by disentanglement. Imagine you are given, I don't know, a photo of anything, so a photo, and then you want to separate it into the specular component, albedo, so all these components that if you compose them nonlinearly, you get back the original picture. Okay, so this is an example of a disentanglement problem, so decomposing, or in 3D. In 3D, you might want to, so if you're working with 3D shapes of a human, maybe you want to disentangle all the variational factors connected to the pose of the human with the factors connected to the style, so to the identity of the human. Okay, so you want to be able to do this distinction. Now imagine you constructed your variational autoencoder. Okay, so you have a latent code for one 3D shape of a human. Now, which dimensions are responsible for the pose? Which dimensions are responsible for the style? Or maybe it is not so sharp. Maybe the two factors of variation, so pose and style, they're not living in different dimensions. Maybe they are mixed all up. They are entangled, right? So you want to disentangle them somehow. So if you see here, when I presented this reconstruction, this interpolation loss, there is also another loss that I'm calling Oh no, I removed it. So there was another term over here that is called the disentanglement loss. Okay, so being able to access the metric of the shape allows you to do the disentanglement of pose and style much more easily. I skipped the details with these slides because it's a bit they're a bit convolved, let's say so. But this is something that you can do easily with geometric shapes because you have access to the metric. This is a true example of the disentangled latent space. Of course, you see the decodings of the latent space, but this is actually the latent space. You see that there is one dimension, which we call extrinsic, where the only thing that changes along this dimension is the pose. The person is always the same. You can look at it here. This person is always the same, but the pose is changing. Same for all of them. And then there is another dimension, which we call intrinsic, where the pose stays fixed and the person changes. So this is true for all poses if you walk along this dimension. Okay, so this is called disentanglement of pose from style. Okay, so this is something you can do in geometric deep learning somehow more easily than with images because you have more metric information you can work with instead of just raw pixels. So maybe maybe this is the key message I want to give you. That geometric deep learning is not necessarily harder. So there are harder parts, for example, the lack of data, that's a problem, but there are easier parts. And this is certainly an easier part that we don't get with images. All right, so a lot of work in geometric deep learning is trying to exploit this extra information as much as possible, maybe to counteract the lack that we have of data and other problems that we have. All right, so one more thing I want to talk to you about is implicit functions. In particular, there is a very rich and very interesting line of research by the group of Yaron Lippmann at the Weizmann Institute. They have been working on implicit functions for quite some time now with a lot of interesting results. So let me show you what we mean by implicit functions, why it is interesting. So another way to look at shapes, well, an alternative representation for shapes is as the level set of some function. So what do we mean? We can regard the shape M, for example, the surface of a cat, as the set of points in 3 dimensions, such that this function f is equal to 0. Okay? So this is a level set 0 for the function f. How does f look like on the rest of the space? So it is 0 at the surface. So what about elsewhere? Well, there are many possible choices. For example, this function f could be the distance to the boundary of the shape, right? So you see that white means 0. So this is the SDF for the hedgehog, 0 at the shape. So it is the 0 level set is the shape. Then we have increasing values outside. They increase with the distance, and decreasing values on the inside. Okay, so they decrease with the distance. It is called signed distance function because we take positive distances over here and negative distances over there. Okay, so you can see easily that the 0 level set is going to be the outline of the shape. Alternative representation. It is called also an implicit representation because we only have an implicit expression for the shape itself. Of course, you can extend this idea to higher dimensions, for example, to surfaces embedded in 3D. You have the 0 level set, which is the car over here. And then we have all these other level sets. They go outward with increasing distance and inward with decreasing distance. Again, signed distance function for a surface in this case. All right, this has nothing to do with learning, right? This is just an alternative representation for shapes, for 3D shapes. And they have been around since forever, basically. And a lot of geometry processing and 3D shape analysis that was done by the end of the 90s, it was dealing with these kind of representations. All right, so now why do we like them? We like them, basically, I can tell you why I like them. So I like them because you don't need to have an explicit discretization of the surface. You never mention explicitly the surface. You only say that it is those points where f is equal to 0. You don't have a mesh. So you only have this function that queries the space and gives you a distance value. If you really want a mesh, there are ways to extract meshes from the implicit representation. This, for example, the marching cubes algorithm extracts a mesh from the implicit representation. In many other cases, maybe you don't need the mesh. For example, if you're doing a rendering application, you can render the implicit representation using ray casting. You don't need a mesh. Why do I like this? Well, because the moment you extract a mesh, you are deciding the resolution for that mesh. You are deciding a quantization for your final object. So this is a hard decision. You want to keep as much resolution as possible. Here you have infinite resolution. The moment you extract a surface, you have to commit to a resolution. Okay, so why am I talking about implicit surfaces? Because recently they have made a return in deep learning, in geometric deep learning in particular. Now imagine the following. Okay, so we have this SDF function. This SDF function is exactly the f that you see here. This f takes as input a point in 3D, gives as output a scalar value, which is the distance to the surface. This is the SDF function. The distance could be positive or negative. Okay, so exterior, interior. Right, now imagine that we make this SDF function, we make it parametric. Okay, so the SDF function is highly nonlinear. Imagine you try to write a formula for it. So this is going to be a nonlinear function. We want to parameterize it. Wait, I see a message on the chat. Oh. Can you still see my slides? Somebody is saying.
Yes.
Yes.
Okay, thank you. So you can parameterize this SDF function with parameters theta. In other words, you can construct a neural network with weights theta that you need to learn that approximates the SDF function for a given shape. Okay, so your neural network is going to be this SDF theta. Okay, so you train it such that whenever you give it as input a point in R3, it gives you the distance to the surface. So this is the way you train it. This way, if you look at the decision boundary of the SDF, so the decision boundary separating exterior from interior of the shape, the decision boundary is the shape itself. This is the intuition. This was the intuition of this 2019 paper, Deep SDF. There are many other similar papers. They changed the implicit function, for example, what was it? Occupancy net. So there are many works that actually all of them from 2019 that did the same thing. So this is the idea. Okay, so parameterize the SDF with a neural network. This is going to be very powerful because then you have this neural network. You can give as input any point in space you want, and it gives you the distance to the surface. Okay, so it stays implicit. You don't need to construct a mesh. In other words, you are representing a 3D object as a neural network. This is a kind of difficult to see for the first time, right? So 3D object is represented by a trained network. They are equivalent representations. Okay, so how do you train it? Well, you train it with pairs, point, distance. Well, it is very simple training. I really don't need to say too much about this. You can regularize the network, well, the training, you can regularize it as much as you want. In what sense? Well, one thing I really want to tell you about is this iconal regularization. But never mind the formulas over here. They're just repeating basically what I already told you. So I told you that the SDF given a point tells you the distance from that point to the surface. Okay. So the image of SDF is a distance field, right? Now, distance equals metric. So you can already imagine that we can apply a lot of knowledge from geometry processing and shape analysis to these ideas. In particular, from shape analysis, we know that distance fields should have the norm of the gradient equal to 1 constantly. What does it mean? So what I'm depicting here is the isolines of the distance field from this curve. So each point on the plane, I compute the distance to the curve. And then for all these distance values, I show the isolines. All points along a gray curve are at the same distance from the gamma. You see that they are equally spaced. They are equally spaced because the distance changes at a pace of 1 meter per meter. This is what it means. And in mathematically, you say that the gradient of the distance function has norm constantly equal to 1. Everywhere you change at a pace of 1 meter per meter. This constraint, the constraint that the norm of the gradient of a function is equal to 1, this is called the iconal constraint. Okay, so if you use it as a regularizer in your loss, we call it iconal regularization. Since you are solving for the SDF and you are imposing this iconal behavior, this constant gradient behavior, then you are really imposing that the SDF you're looking for must be a distance function. Otherwise, it could happen that what you train for, that what you learn, doesn't really behave like a distance function. This could happen depending on how much data you use, training time, and so on, right? So you can add this iconal regularization. Okay, so this is something I think is very important.
Was this picture 2D or 3D?
So this one is 2D.
Right.
In 2D, yes. But
so
yes.
Could it be a projection of some 3D body, and those lines would be then some kind of level set?
So in 3D, you mean? Level set also in 3D?
Yes.
So, okay, no. So in the
I'm trying to imagine this as a projected object on 2D on the plane, but the object that is being projected is a 3D, as you say.
Yes, so there is one very simple example of that. You take a sheet of paper, you bend it like gamma.
Yes.
Yes, and then you look at it from the side, and then you have exactly this projection, right? So you have this curve.
Or I take 2 mirrors and in an angle.
Right. So
and I look at myself.
Yes.
Okay, great. Thank you.
Okay. All right. So what is the problem with this model? I mean, why is it useful in the first place, right? So what we're trying to do, we are given a shape. So the shape is given, right? Because we train with it. We're given a shape and we're trying to learn an SDF representation of it. Why is it useful? It is, well, this doesn't look like a generative model to me. So there is no way in which you can now generate a shape that is different from the one you used for training. So, but this is a very important first step. So let me show you how you can work on this to create a generative model for shapes. So this is what we explained. You have a single shape SDF, deep SDF. So it takes a point, gives you the distance. This is specific for the bunny. The bunny. Now what you can do, if you have multiple shapes, so you have the bunny and the cat, each time you input the XYZ for each point, you also attach a code that tells you this is for the bunny, or no, this is for the cat. Okay, so you attach a code to each input point. Well, this way, the learning model, this kind of encoder that takes as input point and code, is able to distinguish between different shapes. Okay, so before, the only thing it could do was to assume that there is a single shape. And now if you have a code for each of them, you can distinguish them. So you can use the same model to encode multiple shapes, an entire collection. I don't know, all of 100,000 humans. You can do that. Now the question is, well, how do who gives me the code, right? So, well, there is one possible easy solution. The code, I can do it randomly. I can handcraft the code. So bunny is gonna have code 12. Cat is gonna have code 34. Okay, so I handcraft it and then I train with these values. I have perfectly valid multiple shape deep SDF. Or I could make it so that the code are also learned at training time. How can you learn the codes? You can use a trick similar to variational autoencoders. So you impose that the codes must behave according to some distribution. With variational autoencoders, classically, you impose a Gaussian distribution on the latent space. You can do exactly the same here. You can impose a Gaussian distribution on the space of latent codes, and then let the training give you the values to use in the codes. Why is this desirable? Because if you impose a distribution like a Gaussian, then you are imposing some nice and smooth behavior in the latent space. Instead of having codes scattered all around, you try kind of compactify them. And also, you have a distribution that you can sample from. So if you train this thing, they call it an autodecoder. If you train this autodecoder with 100 shapes of humans, then you also learn the latent space with following the distribution. You can now sample this latent space. And then you can decode the code that you have just sampled, and then you get a new shape. Okay, so this is the overall idea. But of course, once again, I'm skipping a lot of details here, but this is the overall idea. So how does it work? It works very well. So look at this. So first row, they trained a deep SDF with this chair, which is more like a sofa, and this chair. And now they do a linear interpolation in the latent space of codes, and they decode. And they get this nice transition from the sofa to the chair. You see? So these are the isosurfaces extracted from the resulting implicit function. Similarly for the car. So they trained with this one, with the leftmost and with the rightmost, and the rest is interpolated in the latent space. So they have this nice smooth transition from one to the other. Okay, so, and of course, so I started this section by saying that this is a new interesting line of research because there are a lot of cool things you can do with this. So if you are from 3D computer vision, or at least you know about photogrammetry or structure from motion, there are a lot of works that model, well, a lot of works, I know two, that model the shape to be reconstructed. For example, the shape of the Colosseum from photos taken from Tumblr. They model it as an implicit function. Okay, so and they follow a model similar to the one I just explained to enforce the reconstruction to look good. I mean, there are photogrammetric losses there and a lot of other things, but this is the idea. So oppose this to classical pipelines where the final reconstruction is modeled as a point cloud by a triangulation. Okay, so you can, if you're familiar with the problem, you can already see that working with an implicit representation instead of a point cloud, which is going to be very sparse, well, this is going to be much better potentially. Okay. Now I want to say a couple of words about graph generation. So we are getting close to the end. So graph generation emphasizes a problem that until now I've kind of kept hidden. Okay, so well, you will see what I mean. So imagine you want to construct an autoencoder for graphs. Okay, so once again, what was an autoencoder? You have as input, you take a graph, for example, the adjacency matrix of a graph, you encode it, you get a code, you decode it, you get again the adjacency matrix for the graph. Ideally, for an autoencoder to behave well, these and these should be the same. So they should represent the same graph. Okay, so this is what we want to do. All right, so it seems easy enough. We construct our autoencoder and then we write down this loss. This is our reconstruction loss. We want the decoding of the encoding of the adjacency matrix to look like the input adjacency matrix. Now, this was actually an exam question for my course on deep learning here in Rome. Do you think that this will work? Or do you see any issue with this process? The question was worth 8 points out of 40. Okay, so no brave student is willing to pass the exam. So the answer is the following. Let's see what I wrote. Okay, so this has a very strong assumption. The assumption that the graphs have the same vertex ordering. So let me explain more clearly. So imagine you have a very simple graph. So a graph with 5 nodes, or well, a graph with 3 nodes, and all of them are connected. So it looks like a triangle. Okay. Now you have an adjacency matrix for this graph, and then you train your autoencoder with these adjacency matrix. So you are able to do the training, everything goes well, and then you have your trained model. Now you give your trained model to your friend, and you tell him, well, this is my trained model. It works very well for graphs that look like a triangle. Then your friend tries with a graph that looks like a triangle and it doesn't work at all. Why? Because the triangle that your friend is using has a different vertex ordering for the 3 vertices. So the adjacency matrix that was constructed is different from the one you used at training time. So this process is assuming that all the graphs that are seen at training time have the same vertex ordering as the ones that will be seen at test time. It is a strong assumption. Okay. You can put it differently. You can say that this is assuming that at test time you have a correspondence, a node-to-node correspondence between the test graphs and the training graphs. And of course, obtaining a correspondence is a known problem. It is known as the graph isomorphism problem. It is an NP-hard problem. So it is a very difficult problem to solve, and this is assuming that you have solved it. Now, of course, that there might be applications where this is not a problem. So in computer graphics, there are applications when where you can assume that you are given the correspondence. But in general, well, if you're working with graphs, generic graphs, this is not going to work. So, and this is why nobody published a paper about graph generation using these reconstruction laws. Okay, so this is not going to work in general. So the idea is the following. This is what has been proposed. Well, one possible solution. So first of all, instead of considering like sharp adjacency matrices, so usually you have binary matrices with ones and zeros, you can use like a soft or a relaxation of the adjacency matrix. So instead of having a 1, which tells you this node is connected to this node, this one now tells you the probability with which they are connected. So for example, this edge appears with very low probability, and this edge appears with very high probability. Okay, so first of all, you can do this relaxation. Why do we do this? Because then we can use continuous optimization, right? So this is something that we like. And this is one possible pipeline. This was proposed in 2018. This was called graph vibe. So the idea is the following. You start with your graph, your input graph. You can represent it as the adjacency matrix, or you can represent it however you want. For example, you can embed it using some graph embedding method. And then you want to construct a decoder that outputs a soft adjacency matrix. So you see, this is representing a soft adjacency matrix. The light gray is for low probability, and the dark gray is for high probability. Then you want to sharpen the adjacency matrix, so you bring it back to the binary setting, so zeros and ones. And then you have to solve a graph matching problem with the adjacency matrix of the input graph. This must be done at training time, solving a graph matching problem. Okay, so well, you want your network, actually, you want an ingredient of your network to be a graph matching solver. Okay. So of course, this is going to be, well, not immediate, not trivial, right? So you want this to be differentiable. So there is no learning here. Okay. So it's non-parametric. You have your graph matching block that goes before the loss is computed. Okay, so you see that this should give you an idea that it is much more difficult than we originally thought. Okay, so now today there are also other approaches, but I wanted to emphasize this correspondence problem. All right, so this is one example of how they used this idea. So they were able to train an autoencoder for graphs. So they have access to the latent space, so they can sample the latent space and decode to a new graph. So they trained on a data set of molecular graphs, like the green ones you see on the left and on the right. And then they are interpolating in the latent space to generate new molecules. Now, of course, whatever molecules you generate, you don't have any guarantee that they're going to be chemically or biologically valid, right? So in fact, the red ones you see here, these are molecules that are not biologically valid. They cannot be realized in real life. So what they proposed, and what actually several people have done later on, is that they add an additional module to this graph by. Imagine that you have an external block that tells you, that informs the network whether the molecule that is generated is valid or not. So you have this oracle, this external oracle that informs the training process. Okay, so this is really helping in generating new valid molecules. And this is also particularly interesting for at least two more reasons. Well, the first one is that graphs are very small molecules are very small graphs. Okay, so you don't really have to care about, so whatever encoder you're using, if you are using the spectral encoder, if you're using some other notion of convolutions, you don't care about the computational efficiency, because with this size, everything can be done very quickly. The second thing is that for this kind of data, molecules in particular, we have a lot of very big data sets from the biological community. There are many open data sets from the biological community. So let me mention just, I don't know, PDB. So if you look for PDB and molecules, you will see that you have access to a lot of information about molecules, their geometric structure. You have a lot of that. So I think this was a very nice application of graph neural networks to the real world. Now, of course, so today we don't have time, but you can generate other representations. So we have seen graphs, we have seen surfaces. You can also generate point clouds. They follow different approaches. For example, a point cloud can also be generated one point at a time, because you don't have any connectivity. So you don't have these additional constraints that you have when you generate something with connectivity. So you can actually proceed one point at a time. So this is a very active area of research today. I would like to conclude with a couple of words about adversarial attacks. Okay, so this is something that we have been interested in for the last couple of years. We think there is a lot of potential in the geometric world, dealing with graphs or 3D shapes, or you name it. So what is the problem? Adversarial attack has been noticed since several years already. So imagine the following setting. You have your autonomous driving car that has a sign classifier, but somebody has attached these stickers on top of the street sign. And now what should be identified as a stop sign is identified as a speed limit. So this is what we call an adversarial attack, and this is malicious, right? So somebody did it specifically. So these stickers are not random, they are computed, they are engineered to lead to fool the classifier. Okay, so this is a malicious adversarial attacks against a classifier, a pre-trained classifier. So this is the setting. Now, of course, this attack is very visible, right? So you as a person, if you see this sign in the street, you recognize there are stickers, you can remove them, and then you're done. So there is no attack anymore. All right, so now how about this? You have your visual classifier, which recognizes these as a school bus and recognizes these as an ostrich. Okay, so what's the problem here? Well, for us humans, we see that these two photos are exactly the same, but in fact, if you compute a pixel by pixel difference, you will see that there are some tiny, very tiny differences in the color values. Now here they are amplified to show them to you, but in fact they are very tiny. So tiny we call them imperceivable attack. We cannot really perceive these differences. And once again, this kind of perturbation, this was specifically engineered. This was optimized for with a specific task of having the classifier misclassify the track as an ostrich. So this was arbitrary, well, it was voluntary. It was done with this target. This is why we call it attack. Okay, so this is different from the example from before, because this is imperceivable perturbation, and this was, well, clearly visible perturbation. Okay, so the question is, how do we look for such a perturbation? So why do I want to generate attacks? I don't want the autonomous driving car to crash, of course, but maybe I want to generate these imperceivable attacks. And then maybe I want to train again the network with the attacked data, so that the network learns that those attacks should not lead to misclassification. Okay, so I can inform the network. This is called adversarial training. All right, so this is just one application of adversarial attacks. There are many other things you can do. Now, we want to bring these ideas to geometric data. Imagine you have your social network, and now you engineer a like button. So I'm going to like that post, specifically because if I do that, then the classifier of who I'm going to vote will be fooled. So this is a very tiny, imperceivable perturbation I do in the social network, just a new edge out of 100 million edges, one new edge that will fool the graph convolutional network. Or on 3D shapes, well, this I can skip. On 3D shapes, maybe I have a pose classifier. This is done, for example, by surveillance cameras or by, I don't know, 3D scanners and so on. They have pose classifiers, or your Kinect. If you play with the Microsoft Xbox, they have a pose classifier that takes 3D data of a player. So they need to be able to distinguish the pose. So you want to imperceivably change the shape such that the pose classifier misclassifies me. See, so this is a wide step pose. Now I'm changing the head a little bit, the foot just a little bit, so that this suddenly becomes a standing pose instead of wide step. For comparison, this is a standing pose in the data set. Okay, so with 3D data and with geometric data such as graphs, we need to redefine what we mean by something that can be noticeable or not. We need to redefine the notion of noticeability. In the case of images, noticeability can be simply captured by the norm of the perturbation in pixel value space. So just the norm, the L2 norm of this perturbation. Can we just apply the L2 norm of the vertex displacement as an idea for noticeability? Let's see. These are the mathematics. I don't think we care too much about this. So the idea is the following. You have, so in case X is an image, the image of the school bus, V would be the additive perturbation on the pixel values, right? And you want to minimize the norm of this one so that the perturbation is not noticeable. Okay, so X prime will look like X, except for a very small perturbation V. Now let's try to do the same, but instead of X being an image, we have X that is a 3D shape or a collection of vertices in space, let's say a point cloud. So V is a displacement field for the vertices in 3D space. And we want the norm to be minimized. So they are displaced just a little bit. So unnoticeably displaced. This is what happens. Look at this. So I'm unnoticeably displacing the vertices of this point cloud. But, well, the very nature of the point cloud, the fact that I recognize this as a human, immediately, for me as a human, immediately I can notice that there are some points out of place. You see, so I see this black dot is outside. So the color I'm using is distance from the original position, just to emphasize it. But these are not unnoticeable for me as a human, right? So this is what we call adversarial jittering. With images, you do not notice this because your eye has some, well, it is not so sensitive in color space. You have jittering in color space with images, but you do not really notice the difference between this green and that green, right? But if that difference is encoding a displacement in 3D space, you notice it immediately. So for geometric data, the classical attacks cannot be carried out. Okay, so you have to do something different. And one thing you can do, well, you can already imagine, you can require the displacement field, the perturbation for the attack, you can require it to be as smooth as possible. Okay, so here is the successful attack on this shape, but now the perturbation is constrained to be smooth. You see, now it is much more difficult to realize that there is an attack undergoing. Okay, so you need this additional regularization. Okay, so how can you do this? How can you regularize for, or how can you ask for smooth displacement? There are many things you can do. One thing we can do is just represent the displacement in the first few eigenfunctions of the Laplacian. If you remember our analogy between the eigenfunctions of the Laplacian and Fourier analysis, you will see that if you only represent a function within the first few eigenfunctions of the Laplacian, it corresponds to a low-pass filtering of the function. So low-pass filtering meaning that you get a smooth function as output. So we parameterized the displacement field for the attack as a low-pass filtering. Okay, so we have a smooth displacement field. So this is exactly what allows us to attack smoothly and not noticeably. So look at this example. So this is the original shape x1, and now we concoct, so we engineer an attack such that x1 will be classified as x2. You see that the pose is very different. The result is this one. So it turns out that the smooth perturbation only changes a little bit the pose of the head and raises a little bit this arm. And now this is classified as x2. Similarly, x1, we want it to be classified as x3, and this is the result. You see, now the head is pointing in this other direction. Okay, so this is a great way, actually, also for images, but maybe even more so with shapes, because we have this smoothness property that we can exploit. A great way to study how your classifiers behave. Apparently, the classifier, the pose classifier that we are attacking, was concentrating on the head position to decide the pose. So this is one possible explanation why this attack is working. Okay, so now what you can do, well, now you can use these two attacks as training data to tell the network that this should not be the case. So you can do adversarial training. So I explained this with shapes because they're nicer to see, but you can do something very similar with graphs. For example, you have, I don't know, the graph of a social network once again, and then you can let your perturbations be edges that you add to the graph or edges that you remove from the graph. And maybe your measure of noticeability is the number of edges that you add or remove. Okay, so there is some work in this direction. For example, the group of Professor Gundemann from TU Munich is working on these adversarial attacks on graphs. So there are a lot of interesting things to do there. All right, so I'm done. So of course, this tutorial, as you can imagine, it's just touching the tip of the iceberg. There is so much material that I had to leave out, and then this area, well, this community is growing very fast. Okay, so there are a lot of directions that are very interesting, and I was not able to touch upon today. One thing I can suggest for sure, if you're interested, is first of all to attend also other tutorials. For example, there are pre-recorded tutorials you can find online by prominent people in the field, like Michael Bronstein or or by Takoho and several others. And definitely one thing I want to suggest is that you download for free this book, as long as it is free. I don't know if, well, this is going to be commercial. I don't know if this is just a window we have for the moment to download it, but this is really new, really recent. So you see that it was finished in 2021. So I'm sure you will find everything you need over here. And with this, I'm done. I will be happy to take questions.
Perfect. First of all, thanks a lot, Emma, for the very, very nice tutorial.
Thank you.
Any remaining questions from the audience?
Yes, I have about the vertex ordering that related to that exam question. And you proposed solution with another network, this solution. I was thinking about maybe I can just do simulation by changing different ordering and then do Monte Carlo averaging and come up with alternative solution to this network.
So it sounds like a possible way to approach the problem. Yes.
Okay, great.
If I may hook in with another question, comparing eigenvalues only is too weak as a loss?
So great question. We are working on that. Unfortunately, well, kind of yes. So there are many more, apparently, there are many more isospectral graphs than there are isospectral manifolds. So you can possibly have an issue there, but we are working on it. It's a good question.
Any further questions?
If there is time, I would ask about the implicit representations. So for the traditional discretizations, we have a sampling theorem that tells us, depending on how fine the features are, how fine we should make our representation. So is there some comparable theoretical guidance of how complex I would have to make the network to represent a certain shape? Or is it this purely empirical at this point?
Okay, so first of all, I have a question back to you. Sampling theorem, you mean uniform sampling theorem?
Yes, so if I just discretize with a uniform grid, the domain, I can apply just Nyquist sampling theorem.
Right, so well, so first of all, yes, there are these nice results, but they only concern the uniform sampling strategy, right? So if you don't have uniform sampling, you have all these L1 magic and so on and so forth that you can appeal to. And so as so your question was, do we only have empirical results as to how complex should the network be? So there are theoretical results. These are called universal approximation theorems. Maybe you've heard of it. So there are some results telling you that certain models of neural networks can approximate any function, well, within some class of functions.
But is this just asymptotically, or does it tell me really how large I have to make it for?
Okay, so some theorems tell you how large you have to make it, but but all of them, I think, don't tell you how you should make it. So there exist activation functions. There exists a dimension for each layer such that this holds. So they are non-constructive theorems. So you know that you can do it, but well, what you can do is empirically see what you get. Well, this is my understanding at least.
Okay, so in practice, you would still try it out empirically, or maybe you have by now some experience or some rules of thumb that you can follow.
We do empirically. Rule of thumb, we don't go too deep. So I think the deepest we go is like 6 or 7.
Okay, this is, I guess, another question. If for a given number of parameters that you're willing to invest, how to distribute them, how wide and how deep.
So usually, yeah. So you can imagine there is no ready answer for this. You ask the Google engineer and he will give you, or she will give you the answer.
All right, thank you.
But maybe if I may jump in again, do you see that you can get better shape representations with fewer network parameters than you would have as a mesh representation or a voxel representation or any other favorite representation of yours?
Fewer network parameters. So I think there is, well, so in general, no. In general, I think you need more network parameters than numbers for representing your mesh. But on the other hand, the meshes we work with have in the order of tens of thousands of vertices. The moment the community starts working with millions and millions of vertices, then maybe we can talk about this again. Yes.
Thanks a lot. Any other questions? Okay, since this does not seem to be the case, again, a huge thank you from all of us to you, Emma. Great tutorial. Jürgen is also there. Perfect.
Yeah.
I
just jump between the sessions to make sure everything works. But it was a really nice tutorial, and thank you, Emanuele, for the time and giving this very, very nice tutorial. Also, I've seen that people were highly interested.
Thank you, Jürgen. Thank you for the invitation to all of you. Of course, this was a great experience. It would have been even greater in person.
Yeah.
Let's try to remedy.
Okay, then perfect. Thank you all. Take care and hope to see you over the next days at GCPR.
Bye, everyone. Thank you.
So no more tutorials today?
Well, this tutorial is at an end, and there was another workshop on scene understanding, but that ends very shortly. So I think for today we're done.
Yeah, there's only the workshop is the only thing what's still running, but it will also then end very soon, maybe in half an hour.